Very good morning, students. Welcome to mathematics class. I am Praveen. Today, we will start this new chapter, applications of derivative. In the last class, we have discussed the continuity and the differentiability topic. Today, we'll start with this new chapter, application of derivative. What is derivative? Derivative is the rate of change of one variable with respect to another variable. Suppose the two variables are changing with if the two variables are changing simultaneously, the rate of change of one variable with respect to another variable is called the derivative. Now we are applying this derivative in some concepts. The first concept that we are discussing is the rate of change of quantities. We are using this derivative in the rate of change of the quantities. Okay, the rate of change of quantities, if y equal to f of x is a function, then here we have two variables, one is y, another is x. Okay, we have two variables, one is y, another is x, and that x is a function here. X is what? It is a function. So y is equal to f of x be a function of x, then dy by dx represent the rate of change of y with respect to x. What is the meaning of dy by dx? Y is changing with respect to x, means the rate of change of variable y with respect to x. Also, dy by dx at x equal to 0, dy by dx at x equal to x naught, dy by dx at x equal to x naught represent the rate of change of y with respect to x at x is equal to x naught. X naught is a real number that we are substituting after derivative. If we calculate dy by dx, that become the rate of change of y with respect to x, and if we substitute x equal to 0, the x equal to x naught, then that become the rate of change of variable y with respect to x at x equal to x naught, x equal to x naught. The next, the marginal cost. We are using the derivative in the case of the marginal cost. Marginal cost. Here, marginal cost means, suppose if you are purchasing this item at 10 rupees, you will not sell this at 10 rupees. You will sell it 12 rupees, 13 rupees, 14 rupees, or 15 rupees. Okay. What is that extra amount? That is a marginal cost. Okay. Here the marginal cost, the given function cost price, a function will be given. To find the marginal cost, we have to apply the differentiation. The marginal cost represent the instantaneous rate of change of total cost at any level of output. If c of x represent the cost function for x units produced, then the marginal cost mc is given by mc, that is dy by dx, d by dx of c of x. Means if we differentiate the cost price, then we will get the marginal cost we will get. To get the marginal cost, we have to differentiate the cost price function. Next, marginal revenue. Next is a marginal revenue. Revenue means income. Revenue is a income. To find the rate of change of income, as suppose if you are selling this kind of items, as the number of sell increases, the profit also increases. The number of sell is decreased, then then what happens, the profit also decreases here. To find the marginal revenue, we are using the derivative as like the marginal cost. Okay, here the marginal revenue represent the rate of change of total revenue with respect to the number of items sold at an instant. R of x is the revenue function for x units sold, then the marginal revenue mr is given by mr equal to derivative of r of x. R of x, suppose r of x is a revenue of the function in which x items are sold. Then if you differentiate that, you will get a marginal revenue of the given function. The next, tangents and normals. You know the tangent means, suppose we have this kind of curve. If a line segment intersecting one point on the curve, if a line segment intersecting one point on the curve, then the line is called tangent. So this is what, this is a point of intersection of the curve and the line, and the line is called the tangent of, a tangent to the curve. Okay, tangent to the curve. At that point, suppose at the point of contact, if we draw perpendicular to the tangent, this is perpendicular to the tangent, this become normal. This is a tangent and this one is normal. Normal is always perpendicular to the tangent. Okay, so we are discussing about the tangents and normal. If y equal to f of x be a function with a graph as shown in the figure, here we have a figure, we have a curve here, we have a curve, and we have drawn a tangent as well as normal here. Consider pq as a secant. If this is a curve, a line segment intersecting the 2 points inside the curve, or if it is touching 2 points inside the curve, then the line is called secant line. Okay, here that pq is a secant line, and q tends to p along the curve passing through the point q1, q2, q3. Okay, q tends to p. Second, pq will become the tangent at p. Here we can draw this kind of infinite lines, like this infinite, we can draw here like this. If we draw a line segment which is coinciding that p and q, here we have, this is p, this is q, p, q, p, q, p, q, many pq lines we are drawing. All these pq lines are secant. Now this is a line segment PQ in which P and Q both are coinciding. Both are coinciding. And this line become the tangent. That line become tangent. And if we draw a perpendicular, to this tangent, that become the normal. By this diagram, it is explained what is tangent and what is normal. Tangent is a line segment which intersecting only one point on the curve, and if we draw a perpendicular to the tangent at the point of contact, then that line become the normal. So you remember that normal is always perpendicular to the tangent. The slope of a line passing through two given points. The slope of a line passing through 2 points. Suppose a line is passing through 2 point x1 y1 and x2 y2. Then the slope of the line is m. It is denoted by m, and the formula is y2 minus y1 divided by x2 minus x1. For example, we have given a line passing through 2 comma minus 1 and 3 comma 4. Then the slope is y2 minus y1. Here y2 is 4, y1 is minus 1. 4 minus of minus 1 is plus 1, 4 plus 1 is 5, and x2 minus x1, 3 minus 2 is 1. That 5 by 1 is equal to 5. This is the slope of the line. But in the slope of the line formula, what is y2 minus y1? The rate of change of y. And what is x2 minus x1? That is the rate of change of x. The rate of change of y with respect to x, it is nothing but the derivative of the function. It means that the slope of the line is nothing but the derivative. The next, the slope of tangent and normal. The slope of tangent and normal. The slope of tangent is, if y equal to f of x be a continuous curve and let p of x1 y1 be a point on it, then dy by dx is the slope of the tangent. Now only I told you here this y2 minus y1 is nothing but dy, and x2 minus x1 is nothing but the dx. dy by dx is nothing but the slope. The slope of the line or the slope of the curve is nothing but the derivative of the function. Derivative of the function, that is tangent to the curve y equal to f of x at point P. Dy by dx at point P is equal to tan phi. If a line is making an angle phi or angle this is angle phi, then tan phi is the slope of the line, or we can say the slope of the curve. Phi is the angle which is the tangent at point P, x1, y1 makes with the positive direction of x-axis. If we draw a tangent, suppose this is x-axis and this is y-axis and this is the curve. If we draw a tangent, to this curve, this line, a tangent line is intersecting a positive x-axis, then that angle is what? That angle is phi. That angle is phi. Then tan phi is the slope of the line or slope of the tangent here. So if we differentiate the curve, definitely we will get the slope of the tangent. Next, the slope of normal. Tangent and normal both are perpendicular to each other. If the two lines are perpendicular, then m1 into m2 is equal to -1. Tangent and a slope both are perpendicular to each other. If both are perpendicular, then their product of the slope is equal to -1. If m1 is considered as the slope of tangent and m2 is considered as the slope of normal, then the slope of normal is equal to -1 divided by the slope of the tangent. If dy by dx is the slope of the tangent, then -1 divided by slope of the tangent, that is -1 divided by dy by dx, is nothing but the slope of normal. To find the slope of normal, first we have to find the slope of tangent, and taking negative reciprocal of the slope of tangent, that becomes slope of the normal. Next, equation of tangent and normal. Equation of tangent and normal. In a straight line, we know that if a line is passing through one point and its slope m is given, the equation of the line is y minus y1 is equal to m into x minus x1. In this, slope of the line is nothing but m, and what is x1 y1? That is the point on which the line is lying. Okay, so the equation of the line passing through the point x1 y1 and having a slope m is y minus y1 equal to m into x minus x1. Suppose if it is a equation of the tangent, then m become dy by dx. Then the equation of tangent become y minus y1 equal to m is nothing but dy by dx into x minus x1. That is equation of tangent. And normal is perpendicular to tangent, and slope of the normal is -1 divided by dy by dx. So equation of the normal become y minus y1 equal to the slope of the normal is -1 divided by slope of the tangent into x minus x1. Okay, so using this formula we can find the slope of the tangent, and using this formula we can find the slope of the normal. Understood, student? So this is what we are applying the derivative. In the solving the equation of line or equation of tangent or equation of normal. So this is application of derivative. So now we are discussing another concept in this application of derivative, that is increasing and decreasing function. Increasing function and decreasing function. Suppose if a line is increasing like this, then this kind of function is called increasing function. if another curve is given like this, then this kind of function is a decreasing function. Decreasing function. If we have a curve like this, it is increasing, both increasing and decreasing, and then this kind of a curve is called neither increasing nor decreasing. Neither increasing nor decreasing. But if this curve, if we split this curve like this, in this interval this curve is increasing, and in the next interval that curve is decreasing, but throughout the interval it is neither increasing nor decreasing, that we have to consider. Okay. So this increasing and decreasing is calculated by the derivative only. By the derivative, we are calculating this increasing and decreasing, the point of increasing, where it is increasing, where it is stopping. Okay, that everything we are discussing in this increasing and decreasing function. Okay. So you can see that this is what it is, increasing curve, increasing function, and this is what decreasing function, and this function is neither increasing nor decreasing. This kind of graph is called a constant function. Constant function it is. Okay. Now let I be an open interval. I be the open interval contained in the domain of real valued function f. Suppose we have a function f. We have a function f, and I is the interval which is in the domain of the given function f. Then f is said to be increasing on I. In the given interval, we can say the given function is increasing function. When we can say increasing function, if as x1 decreasing, or x1 is less than x2, if x1 is less than x2, then f of x1 is less than or is equal to f of x2. If we consider a 2 point x1 x2 which is in the interval, which is in the given interval of the function f, and x1 is smaller than x2, then f of x1 should be less than or equal to f of x2 for all x1 x2 belong to I. Then we say that the given function is increasing function. See, this is x1, f of x1 is smaller. If this is x2, f of x2 is greater. F of x1 is smaller than f of x2. Okay, then the function is goes on increasing here, goes on increasing here. If this point is x1, this is f of x1, this point is x2, this point is f of x2. As x1 is less than x2 and f of x1 is greater than or equal to f of x2, then the function is called decreasing function. Decreasing function. Okay, in this we have one more concept, that is strictly increasing and strictly decreasing. Okay, here if f of x1 is less than or equal to f of x2, then the function is called increasing function. If f of x1 is less than f of x1 is that is f of x1 is less than f of x2, then it is called strictly increasing function. What is that? F of x1 less than or equal to, then increasing function. F of x1 is less than, then it is called strictly increasing. Strictly increasing function. Okay, and decreasing means f of x1 is greater than or equal to f of x2. Decreasing function. If f of x1 is greater than f of x2, then it is strictly increasing function. Theorem. Let f be continuous on the closed interval a comma b and differentiable on open interval a comma b, then f is increasing in the open interval a comma b if f dash of x, if this f dash of x is greater than 0 for each x belong to a comma b. Suppose we have given a function f of x, and this function is said to be increasing function if the derivative of the function is positive. If the derivative of the function is positive for every point in the interval a comma b. open interval. See here, any function if it is continuous in the closed interval a comma b, then it will be open interval in the differentiable at open interval. Remember this point. Okay, when we are differentiating the function, the closed interval become open interval. You know the difference between closed interval and open interval? Closed interval mean the end point in this interval are also included as a point. But in this open interval, the end point A and B are not included as a point. Okay. So therefore, if the derivative is greater than 0, then the derivative of the function is greater than 0, then the function is called increasing function, and derivative is less than 0, mean negative. If the derivative is negative in this interval, then we can say that the given function is decreasing function. If derivative is equal to 0, if the derivative is 0 for each x belong to a comma b, then the function is called constant function. This function is called constant function. Next, maximum and minimum value of the function. Maximum and minimum value of the function. Suppose we have given a that is x greater than 2. If we write x is greater than 2, the greater than 2 real values are 2, 3, 4, 5 and so on. Greater than 2, it means it start from 3 or 2.1 or 2.01 something which is greater than 2. If it is greater than or equal to, then only it start from 2. If we have a x greater than or equal to 2, then the value starting from 2, 2, 3, 4, 5. Here there is no maximum value here, no maximum value. But we have a minimum value. If there is greater than symbol, then there exists minimum value. If there is smaller than symbol, then there exists maximum value. The symbol is quite here opposite. If we have greater than symbol, then there exists a minimum value because it start from that point or it start from that value. That's why it has minimum value. If there is a smaller than symbol, then that value ends there. That value ends there. It means that that is a maximum value. So minimum is not defined here. Let f be a function defined on an interval I, then f is said to have a maximum value in I if there exists a point C in I such that f of C is greater than f of x, and x is belong to I, then the number f of C is called the maximum value of f in I, and the point C is called a point of maximum value of f in I. So I told you, if you take a point that is x greater than 2, the values are starting from 2 here, then there exists a minimum value. If we have a x less than 2 or less than or equal to 2, then maximum value is 2 here. Suppose if we take a point C, which is in the interval I, and f of C value is greater than all f of x, f of C value is greater than all f of x, then f of C then that f of C value is a maximum value of f. F of C is maximum value of f. At C, if we are getting two value, if C we are getting two value, for other value we are getting 1, 0, minus 1, minus 2 something, then this is f of C value. It means that there exists a maximum value. At what point we are getting 2, then the point is called the point of maxima. The point of maxima. The point is called maxima and the value is called maximum value. And minimum also. And the minimum also, if f of C is smaller than f of x, then f of C is minimum value of the given function f, and the point C is called the minima of f. If f is said to have an extreme value in I, if there exists a point C in I such that f of C is either a maximum value or a minimum value of f in I. The number f of C is called an extreme value of f in I, and the point C is called extreme point. If it is increasing or decreasing, if the function is both increasing and if it is both increasing or decreasing, then it's said to have extreme value. It have a extreme value like this. It have extreme value. If it is either increasing or decreasing, then that function having a extreme value. Extreme value. So the point is called extreme point and the value is called extreme value of the given function. See, here only increasing at this point we have maximum value and the point is called maxima. Okay, if the curve is like this, if the curve is like this, and here we have a minimum value and the point is called the minima. If we have a curve like this, then this point this curve having a extreme point, this curve having a extreme point, and the value is called extreme value. The next, critical point. Critical point. Suppose our curve is like this or like this. At this point we have maximum value, at this point we have minimum value. Okay, the point where the curve showing a maximum value, that point is called a critical point. That point is called critical point, or a point where showing its minimum value is called critical point, where the curve changing. Means what happening here, the curve is goes on decreasing, but at this point the curve becomes stop, and that point again it goes on increase. The point where the curve stop increasing or decreasing, the point is called critical point. What we call the point? Critical point, where the curve stop decreasing or the stop increasing. Okay, the point is called the critical point. Next, the first derivative test. First derivative test, here we have a two derivative test for finding a maximum and minimum value. This is the first derivative test of finding a maximum and minimum value. This first derivative test says that let f be a differentiable function defined on the interval I, and let a is belong to I. We are considering a point A which is in the interval I. Then x equal to a is a point of local maximum value if f dash of a is equal to 0. F dash of a equal to 0, and f dash of a is equal to 0, and what is this? Local maximum value. Local maximum value. So here the curve have increasing and it is this decreasing. At f dash of a, this point becomes 0. Okay, and this point is called the local maximum value of f. What we call the local maximum value of f, and the point is called the local maxima. The point is called local maxima. So f dash of a equal to 0, on taking f dash of a equal to 0, we'll get what? Here the point, critical point we will get, and the point is called the local maxima and the value is called local maximum value of the given function. If f dash of x changes sign from positive to negative as x increases through a, then f dash of x is greater than 0 at every point sufficiently close to and to the left of a, then f dash of x greater than 0 at every point sufficient to closed and the right of a. Means the value is increasing as x is decreasing here. The value is increasing. देखिए f dash of x is greater than 0 at every point sufficiently closed and to the left, means x decreasing, f dash of x is increasing. Then there exists a local minimum value. There exists local minimum value. Okay. Because greater than 0, then minimum value, less than 0, then there exists maximum value. At x equal to a, the point of local minima value, if that f dash of a is equal to 0 and f dash of x changes sign from negative to positive, negative to positive, it is increasing, then there exists minimum value. The point is called local minima and the value is called local minimum value. Okay. If f dash of a is equal to 0 and f dash of x does not change the sign as x increasing through a, or it does not changing sign positive to negative, negative to positive, then the point is called the point of inflection. For example, f of x is equal to 2x, then what is f dash of x? F dash of x is 2. If you take x0, x1, x2, x3, then the derivative does not change. Negative to positive, positive to negative, it will not change. It means that the point is called the point of inflection. अगर वहाँ x की वैल्यू पुट करने से if it is not changing, then we can say the point is point of inflection. So you scroll this video slowly, then you can note down all these points. By knowing all these points, you come to know what is local maxima, local minima. Okay, to find a maxima and minima, we have one more concept, that is second derivative test. Second derivative test. What is second derivative test? How to apply that we will discuss here. Let f of x be a function defined on an interval I and c is belong to I. Let f be twice differentiable at c, then x equal to c is a point of local maxima if and only if f of c, f dash of c equal to 0 and f double dash of c is less than 0. Means we have given a function f of x, you differentiate that. On differentiation, you take this value equal to 0, then you will get x equal to a point called the critical point. And find the second derivative here. If the second derivative at x equal to c is less than 0, second derivative at x equal to c less than 0, then there exists a local maximum value and the point is called local maxima. Okay, and f double dash of c is greater than 0, then there exists a local minima, minimum value and the point is called local minima. The test fails, the second derivative test fails if the second derivative equal to 0. If you differentiate the function twice and you are getting 0, if you are getting 0, it means that the second derivative test fails. By the first derivative only we come to know that which value, whether maximum value is exist or minimum value is exist, that can be identified here. So this is called the second derivative test. Here given one example, find the local maxima and minima of the function f of x is equal to 3x power 4 plus 4x cube minus 12x square plus 12. We are finding the local maxima and local minima of this function. Okay, so for the solution we are differentiating this function. F of x is 3x power 4, 4x cube minus 12x square plus 12. 3x power 4 derivative is 12x cube, 4x cube derivative 12x square, minus 12x square derivative is minus 12x and plus 12 derivative is 0. Taking this derivative, first derivative is equal to 0. In these three terms, 12 is common. What is remaining here? X square. 12x is common. On taking 12x common, remaining here x square, x minus 2. X square plus x minus 2 is what? It is a quadratic equation. On factorization, we will get here x minus 1, x plus 2. Then the total expression become 12x into x minus 1 into x plus 2 is equal to 0. We are taking f dash of x equal to 0. Then we have three critical points. So 12x equal to 0, then x equal to 0, x minus 1 equal to 0, x equal to 1, x plus 2 equal to 0, then x equal to minus 2. We have three critical points. We have three critical points. At these three critical points, we have to check the values. Okay, we are not using here second derivative test. We are not using the second derivative test to find the local maxima and local minima because we have 3 points. Okay, we are substituting all these 3 points in the given function. Okay, if we substitute all the three values, then we'll get all the 3 points, then we will get three values. If we substitute these 3 points in the given function, we will get 3 values. Among these 3, the smaller one is a local minimum value and the point is called the local minimum value. And the maximum value is called the local maximum value and the point is called local minima. Okay, local maxima, sorry. So, we have 3 points. So here he is calculated by the second derivative test. By the first derivative test also we come to know that it is maximum, its maximum and minimum value. So second derivative he has done here. This critical points we got by the second derivative test. F double dash of x. This is f dash of x. 12x cube derivative is 12 3 is a 36x square. That is 36x square, and 12 to the 24x and minus 24. In these three, 12 is common. 3x square plus 2x minus 2. At x equal to minus 2, then the f dash of minus 2 become positive and it is greater than 0. At x equal to 0, you will get minus 24. We will get minus 24 less than 0. At f dash of 1, f double dash of 1, we are getting 36 positive. Therefore, by the second derivative test, x equal to 0, at x equal to 0 is the point of local maxima. The second derivative value we are getting minus, then there exists maximum value. That exists local maximum value. This point is called local maxima, and on substituting x equal to 0 you will get 12. That is the local maximum value. Okay, and f double dash is less than the minimum value at it is 2 points. It is minimum value, that is x equal to minus 2 and x equal to 1. X equal to minus 2 it is 72, x equal to 1 it is 36. At 2 point it has a local minimum value. So that these 2 points are called local minima and the values are called local minimum values. So that point we have to substitute in the given function. That point we have to substitute in the given function. So this is the way we are finding the local maxima and local minima. Let us start the problems here. We will solve the problems. Find the rate of change of area of circle per second. Finding the rate of change of the area of circle per second with respect to its radius r, with respect to its radius r equal to 10. You know here area of circle formula is pi r square. With respect to its radius we are differentiating, then this become dA by dr is equal to pi as it is r square derivative 2r. At r is equal to 10 centimeter. Actually this is the rate of change of area, but we are finding the rate of change of area of circle at radius 10 centimeter. Okay, at radius 10 centimeter, this dA by dr become 2 pi into r value is 10, and what is 2 tens? 20 pi. This is the rate of change of area of the circle at r is equal to 10 centimeter. 20 pi it is. 20 pi, you can see that this first option is correct. Understood? So this is a rate measure problem. This is what the rate measure problem that we have discussed in the application of derivative first topic. Okay, the next we will move to the next problem. A stone is dropped into quiet lake and waves move in a circle at a speed of 4 centimeter per second. Here, suppose we have a quiet lake and we are dropping a stone in that. Okay, in that lake, if we are dropping a stone, what happen? The waves are moving like this. At circular, it moving. Correct? Na? Okay. This is a point of stone where we have dropped the stone. Okay. Uh, at an instantaneous speed is given. What is that speed of 4 centimeter per second? The speed of this wave is given. It is nothing but the radius. The speed of wave is nothing but what? It is the radius. Radius is moving. Speed of wave is nothing but the radius. From this point, like this circle is moving, means this is what the radius. The rate of change of radius is given. That is how much? 4 centimeter per second is given. The rate of change of radius is given 4 centimeter. And which shape it is forming? It is forming a circular shape. Then area of circle formula, that is pi r square. Pi r square. Then we are finding the rate of how fast is the enclosed area increasing. So we are finding the rate of change of area. That is a dA by dt. dA by dt is equal to pi is a constant as it is. R square derivative is 2r dr by dt. In the previous question we have not written dr by dt. Here we are differentiating with respect to time. That's why we have written dr by dt. But the previous question we have differentiated with respect to r. With respect to r it become dr by dr. So dr by dr is 1. So we have not written that. Now we are substituting all the values in this. That become 2 pi r. R is given 10 centimeter. And dr by dt is given 4 centimeter. Then this become 4 to the 8. 8 tens are 80. 80 pi centimeter square per second. Means the enclosed area increasing 80 pi centimeter square per second. If the radius is changing 4 centimeter per second, then the area increases. The area increases 80 centimeter square per second. So this is the rate of change of increase in the area when the radius is 10 centimeter. Clear? So in this way, we have calculated these two problems based on the rate measure. Okay, students, today we will stop our discussion here, and tomorrow we will discuss some more questions. You run this video slowly, understand all the concept of application of derivatives, and try to solve these problems. So I have already explained these two questions. You go through all the topics and solve yourself these two problems. After that you check your answers. Okay. So what is our last answer? This is 80 pi. We have not marked our answer here. This is 80 pi. So you solve it yourself and check once again your answers. So here if you solve yourself, then you will get a confidence of getting good marks in the CUET examination. Okay students, we stop here. We'll come back in the next class. Thank you.